All right, so we just finished letter D, and we're now going to go on to question E. Determine if the sequence converges or diverges. If it converges, find the limit. And the method we're going to use here is what I call, what did I call it? Some form of trickery. Crazy trickery. So how can we use crazy trickery? Hey, come back. To determine if this sequence converges or diverges. So the trick to this one is, what I notice is that each part of the sequence just adds on another term. So I start with 1 over 1 times 2, and then I add on 1 over 2 times 3, and then I add on 1 over 3 times 4. And I can actually rewrite this doing a similar type of thing like I did for partial fractions. This is 1 over 1 minus 1 over 2. And if you don't believe me, if we tried to combine these two fractions, we'd multiply here by 2 over 2, and here we'd multiply by 1 over 1, and we'd end up with 2 minus 1 on the top, which would give us 1. And similarly, 1 over 2 times 3 is 1 over 2 minus 1 over 3. And again, if I multiply here by 3 over 3 and here by 2 over 2, I would end up getting 3 minus 2, which is equal to 1 on the top, and then a 2 times 3 on the bottom. So this whole expression can be written out in the following manner. It's 1 over 1 times 2. And then this next one, instead of 1 over 1 times 2, I'm going to write it as 1 over 1 minus 1 over 2 plus, and then this next term that was the 1 over 2 times 3, I'm going to write that as 1 over 2 minus 1 over 3. And the nice thing about this is we notice that the 1/2s would cancel. And this whole thing here would simplify down to 2/3. This thing would simplify down to 1/2. And then for this big one, I would end up getting 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3. That's what I had before. And then the 1 over 3 times 4, that's the same thing as 1 over 3 minus 1 over 4. I could put all these in parentheses if that would make you a little bit happier. But once we remove the parentheses, just like we saw before, the 1/2s will cancel, the 1/3s will cancel, and I'll be left with 1 minus 1/4, which of course is just 3/4. So this whole sequence is really equivalent to the sequence 1 minus, I guess for each of these, it's going to be, this is where I've got n equals 2, and I'm doing 1 minus 1 over 3, so it's 1 minus 1 over n plus 1. And when I have n equals here, this is for n equals 3, and I'm doing 1 minus 1/4. So the crazy trickery that I'm talking about here is rewriting this sequence into a nicer form. And now it's really easy to take the limit as n goes to infinity of 1 over 1 minus n plus 1. The 1 over n plus 1, well, that just goes to 1 over infinity, which is 0. So this limit just equals 1. And the reason I call it crazy trickery is because there's no obvious way you could tell right off the bat that this particular sequence, you're going to be able to rewrite it in that form. And if you just started calculating out what each of the terms were, you might notice the pattern that the top entry is increasing by 1 and the bottom one is also increasing by 1. So an equivalent way of writing this is it's n divided by n plus 1, but justifying that that's what it would equal is a little bit complicated, and what I just did here is the way you would justify it. All right, Letter F, determine if the sequence n plus 1 factorial over 7n factorial converges or diverges. And for this one, I told you to just simplify the expression. So we can think here, let's just suppose we gave n a value, like n equals 5. Then this would be 6 factorial divided by 7 times 5 factorial. 6 factorial, of course, is 6 times 5 times 4 times 3 times 2 times 1. 7 times, and then 5 factorial is 5 times 4 times 3 times 2 times 1. And you notice that the 5, the 4, the 3, the 2, and the 1 all cancel out. And I'm left with just, in this case, a 6 over 7. And in fact, I can rewrite this entire expression to be n plus 1 times n factorial. Because the n factorial is going to give me the n times n minus 1 times n minus 2 all the way down. And then when I put that over a 7 times n factorial, my n factorials will cancel. Ta-da! So again, this sequence is just equal to n plus 1 over 7. And if I take the limit as n goes to infinity of n plus 1 over 7, I just get infinity. So this, in fact, diverges. There is, in fact, no limit. So go ahead and try to work on exercise 15 on your own. See if you can figure out for what values of r this particular sequence is convergent. And I recommend you try a few different values of r and see what happens, and then see if you can figure out the general rule. Let's go ahead and pause the video now and try to work on that one. And when you get stuck or done, unpause the video. Okay, so I'm going to start by just, I don't know, trying some numbers. So suppose r equals 2. Well, then my sequence is 2 to the n. And that seems like it's probably going to diverge. And it does. You get 2, then 4, then 8, then 16, then 32. Each time you're going to be multiplying by 2 when you increase n. So that totally diverges. And it's pretty easy to see that any r value bigger than 2 is also going to diverge. Now, how about if I did something smaller, like 1 to the n? Well, 1 to the n is just 1. So this is just going to give me 1, 1, 1, etc. That's going to converge to 1. So I think, oh, maybe I've got something in the middle between 2 and 1 would work. Let me try 3 over 2 to the n power. This is going to give me 3 halves, then 9 fourths, then 27 eighths, then 81 over 16. This really looks like it's going to be increasing to infinity, which is exactly what it does. And the reason is that each term, I'm multiplying it by another 3 halves, so it's getting bigger. And it's just going to keep getting bigger and bigger and go off to infinity. And in fact, that's going to be true for any r that's greater than 1. Because it's always going to be getting multiplied by something greater than 1, so it'll keep increasing. So I know if r is greater than 1, it diverges to infinity. Now, how about for things that are less than 1? So suppose I did, I don't know, 1/2. Well, that's going to give me 1/2, then 1/4, then 1/8, because this is 1/2 times 1/2, 1/2 cubed. That's just going to keep getting smaller and smaller, and it's going to converge to 0. And hopefully you can see that for any fractional number between 0 and 1, it's going to just keep decreasing because you're multiplying it by something that's less than 1. So if you're multiplying by something less than 1, it's going to get smaller. So what do we have here? If r is between 0 and 1, then it converges to 0. And if r equals 1 converges to 1, but I never said that r had to be a positive number or 0. It could be negative. And hopefully you'll see that if we have any negative fraction, so something like negative 1/2, maybe I'll just do that real quick, change some of these numbers here. If this was a negative 1/2, I'd start with a negative 1/2, then I get 1/4, then negative 1/8. It would bounce back and forth, negative to positive, but it would still converge to 0. It would just come from both the negative and the positive side. So I'm going to put a negative 1 on this other end here, and all of those are going to converge to 0. What happens at negative 1? Well, if I do negative 1 to the n power, I'm going to start off getting a negative 1, then negative 1, then 1, etc. It's always going to bounce back and forth. So that's going to diverge. So these are our values for when it's convergent. And if r equals, I guess if r is less than or equal to negative 1, or r is greater than 1, then it diverges. All right. Theorem 5.1. Every bounded monotone sequence converges. So the important thing here is to figure out what exactly these terms mean and give you a rough sketch of why it will in fact be true. So bounded means that there's some number that's always going to be greater than every single entry in the sequence. And actually, if it says bounded, that means both bounded above and bounded below. So some number is greater than every entry in the sequence. Maybe I'll call this greater number g than every entry in the sequence. And some number is also less. Maybe I put this g in the wrong place, really. I should say some number, which I'm going to call g. And here's some number L is less than every entry in the sequence. That's what it means to be bounded. You've got something always above and something always below. Now, how about monotone? Monotone means it's always either increasing or it's always decreasing. So I'll just say it goes in one direction. So always increasing or always decreasing. So the idea here, if I wanted to show this graphically, is suppose I had some value g, and these dots represent the values in my sequence. These would always have to be less than g, and because I'm monotone, this is going to keep increasing. And basically the idea is it's either going to level out somewhere before it gets to g, or it's going to level out when it gets to g. It will continue increasing, but very, very slowly. And it'll basically look almost like g is like an asymptote, a horizontal asymptote. And so if that's the case, if it's an asymptote, then this sequence is going to converge to it, or converge to something less than it. And the similar diagram goes in the bottom. So what happens if you have a bounded sequence that's not monotone? So let's do this one. You may have seen it before. Sine of n. So this one here is bounded because it's always greater than or equal to -1, but of course less than or equal to 1. but it's not monotone because it bounces up and down. So, and in this case, we can say that it diverges. On the other hand, I could have the function sine of n divided by n. And that's going to look similar to that one above, but because I'm always dividing by n, as I go further and further out, my humps get smaller and smaller, right? This top thing, the sine of n, is bounded by 1 and -1, and this bottom number is just going to go to infinity. So sine of n over n, it's also bounded. It's not monotone, but it does converge. So just because I don't have one of these, the bounded or the monotone, does not guarantee that I will not converge. If you're not bounded, though, then you're definitely not going to converge. And the reason for this is if you have a limit that you're approaching, at some point you have to get close enough to that limit, right? So if you think of a sequence sort of coming like this, and it's approaching a limit L, the definition of the limit says you have to get sort of within a certain range of this for all values that are big. And if that's true, if I'm always within this range, then I have a finite number of other points out here that I should be able to choose some bounds above and below, my g and my greater than and less than. I used L twice here. One is for the limit and the other is for the less than bound. And so I should always be bounded if in fact I have a limit. So not bounded means does not converge, but not monotone, it could converge or it could diverge. If you have both bounded and monotone though, you are guaranteed in fact to converge.